So today our topic of discussion is polarization. So that is a property of light. So before coming to that, so let us recap so far what we have studied. In geometrical optics, we consider light as a ray, and the property we assume there that light travel in a straight line or light rays travel in a straight line, and it always remain and it's bent basically during reflection and refraction, but after that again it start moving in the straight line only. We also read in our physical optics part that light is actually behaving like a wave, and the proof behind that is that light source. So light is the wave, and what was their proof? Proof was Young double slit experiment and diffraction experiment. So YDAC, Young double slit experiment is an interference phenomena, and there is also diffraction. These two phenomena prove the light is actually a wave. Now, during our wave chapter in class 11, we classify waves uh, in types. Like we classify waves into mechanical wave and non-mechanical wave based on is the wave required any medium or not. So wave we classify as mechanical and non-mechanical. Non-mechanical. In mechanical there was sound, it need medium, and non-mechanical there are electromagnetic wave that don't need any medium to travel. It can travel in free space. And in our electricity magnetism chapter, so there was a dedicated chapter for electromagnetic wave. So we learned and that light is a electromagnetic wave. So it's a non-mechanical wave. Now we also classify waves in another two parts based on how the particle of the medium oscillate. If the particle of the medium oscillate in the direction of propagation of wave or in the direction parallel to the propagation wave, then we called it longitudinal wave. For example, sound wave is a longitudinal wave, and we also then there was transverse wave. Then there is transverse wave. So where the particle of the medium oscillate perpendicular to the direction of propagation of wave. Like very common example is sea wave or water wave, and so this is a very common example. Now question is that if the light we so far understood is a wave, and then we also understood light is an electromagnetic wave. Now what type of wave light is in terms of is longitudinal or transverse wave? So light is basically a transverse wave, and proof of that is polarization. I going to come to that, how polarization, which is a new property of light, which we're going to study, relating that or proving that light is a transverse wave. Anyway, so first discuss our the most appropriate answer, at least in your level. If someone asks what light is, you're going to say that light is a EM wave. And your concept, this idea going to shatter again when we study the quantum theory or quantum physics. But for now, we will consider light is an electromagnetic wave. In it, we know that let's say this is the direction of propagation of light. Light is going in that direction, and then this light wave is consist of an electric field which is varying with respect to time. Also perpendicular to that electric field, there are also magnetic field. So this is B and this is E. So you can think this is a ray of light we are representing, or sometimes we call this type of representation is a plane wave representation. So here electric field is oriented in a particular direction, actually oriented in a plane of the paper or plane of the board. Now if we have a random source of light, let's say a light bulb, it produced light waves. Now if we look here, let's say let me focus in that direction. So lots of light rays or light wave going in that direction. Then some of the ray have electric field oscillating in that direction, plane of the page. Or maybe there is possible a light wave or light rays for which electric field oscillating perpendicular to the page. And you can think all sorts of angle in which electric field can oscillate. And perpendicular to that, there is also a magnetic field that I am not writing down, that will complicate my picture. So for a light source, usually light coming out of it, when light coming out of it, the electric field, it has different rays or different waves having electric field orient in every possible direction. This type of light we called unpolarized light. So that's a unpolarized light. So electric field are oriented in all possible direction and light is traveling in that direction. Now if the electric field of the light wave is oriented to a particular direction in all the waves coming out from a source, then we call light as a polarized wave. So like this is the direction of propagation. Now it is possible that here electric field are only oscillating in the plane of the board. This picture is similar to the initial wave I draw here, where electric field is oscillating in the plane of the page or plane of the board. It is also possible that your electric field oscillate perpendicular to the page. So here light are polarized. So both are actually called plane polarized light. So now for this type of light, if you imagine here, if the light rays coming towards our eyes horizontal to the ground, in this case actual electric field oscillate parallel to the ground. So this type of light rays sometimes called horizontal polarized light. So let's say someone is here, a light rays is coming and electric field oscillating like this. So this is ground, that means electric field oscillating parallel to the ground. So it is your horizontal polarized light. Now again let me consider another ray when electric field oscillating like this, which is perpendicular to the ground. So this is vertically polarized light. So this one we just a special name, but most important case is the both are plane polarized light. That means the electric field of electric field oscillation is confined to a plane. This is vertical. Now how to make a polarized light? So let me consider there is some kind of a black box first and unpolarized light going into it, and coming out, let's say a plane polarized, which is in this case is actually a vertically polarized light. For now, consider it's a plane polarized light only. Now, let me first tell you a story, an interesting story, a funny story I can say. You can think like this black box is a political rally where a minister is there or a big political big shot is there, and now people of different mindset attending this rally, some out of curiosity, some actually out of free food and all, or maybe some out of money. So they attending the meeting, and they does not made their mindset anyway initially to whom give a vote, etc. Now the black box here, or which is the leader, gives some speech, hot speech, and people get polarized and they all think that we are going to now vote for this leader. Okay, so they are coming out of polarized. So we are aware of this political polarization. It's a common term in media. So you can think like that. Whatever the black box or polarizer, that is basically helping us to orient all these randomly oriented electric field in a particular direction. But now we can make a very simple analogy of this black box, what is actually happening. So you can think first, this black box is a fence. Now there are rods aligned uniformly, closely spaced. Now we put a string through it, and this side we attach, and this side we are creating vibration. We are making this side up and down, up and down. As a result, we are going to create a wave pulse which is going to travel through the uh, travel through the string and reach the dead end. Here is a rigid support. Now, if I oscillate in the parallel direction to this fence bar, the waves will go up and down and pass through the fence and come this side. The wave will reach here. But if I oscillate like this, now it will oscillate in that direction, and the oscillation will feel a resistance in the bar, and they stop. And this side we almost get nothing or a very small oscillation. So here, this nice alignment of fence actually choosing the oscillation direction. So we can think inside the black box also this type of thing is happening, and this thing we call polarizer. So that polarized our light. So you can think it is like our political leader. So there are several ways to make the light polarized anyway. So in our sunglass there are Polaroid sunglasses available. So on there are some kind of a film which polarize the light. Also there is something we call nickel prism that polarize the light. In ordinary days, we can also make light polarized if it is reflect from a surface, a water surface or glass surface or mirror after certain angle. With a certain angle. So that we are going to discuss a bit. Now, question is that, so I am initially start our discussion that polarization phenomena actually prove that light is a transversal. Now, we can, from this example, we can basically perform this demonstration. We can explain that light is a transverse, or light is a longitudinal wave. Now, if a longitudinal wave pass through this fence, let's say now we have a spring kind of a thing. The thickness of the spring such that it is very easily pass through the fence bar. Now, if we just little bit increase or decrease the spring, now a longitudinal wave, that means a series of compression, rare refraction travel through the spring without any obstacle. we assuming with the assumption that the thickness of the spring is less than this bar separation. Now, so here the wave in the spring is a this wave in the spring is a transverse wave. Now, if I now take the spring and oscillate like the string before, now it will allow the wave in when we are oscillating in that direction, whereas restrict when we are oscillating in perpendicular direction. In the second case, we are actually creating a transverse wave in the spring, and we are the intensity of transverse wave, the amplitude of the transverse wave in other side is controlled. How the wave is, what is the amplitude direction, or you can think we are always oscillating in the same direction. We can rotate the window to restrict the wave. So this phenomena actually we can see also in the case of light also. So what we do, actually we take initially a thing called a polarizer, let's say, which is orient light in that direction, and initially we pass through it, pass the unpolarized light through it. If we take any ordinary source, sunlight, any bulb, it will in general produce unpolarized light. After that it will become polarized. Now we are going to put another window or another polarizer here. Now if I allow to rotate it, we are going to see intensity here. Let me call it I prime, which is varying, which is changing. Basically this I prime become a function of theta, where theta is the angle with which this we are rotating the polarizer with respect to this. Initially we can think both axes are parallel and we are rotating this. This phenomena that the rotation of this window controlling the intensity of light, indicating that light is a transverse wave. If light is a longitudinal wave, this phenomena we are not going to observe. The particle or electric field will oscillate parallel to the direction of propagation, and they will easily pass. Anyway, so this is one thing I want to say. Now move on to something, how to make a polarized light very easily. First discuss, we called Brewster angle and Brewster law. Brewster law and angle. So it was known, and people before Brewster also observed, that when light incident on the surface, on some surface, after reflection, the light ray become polarized either wholly or partially. And Brewster actually, when he aware of this, he performed very precise experiment, and he observed for a certain angle the ray become completely polarized, and at that scenario the angle between the reflected light and the refracted light is 90 degrees. So when the angle between the refracted rays and reflected rays is 90 degree, at that time Brewster observed that reflected light is 100% polarized, or you can say nearly wholly polarized at least. So this is incident ray, and this is a refracted ray, and this is reflected. So this is, we are studying basically polarization by reflection. By simple reflection we can polarize our light. So here sorry, my bad, light ray, the polarized light, the polarization plane of the light will be lie in the same plane of the plane of incident. So plane of incidence is constructed by, we are already aware of this, angle of incident and the normal. So here the plane of incident is basically our plane of the board or plane of the paper, and light ray will oscillate in the same plane, and this is the direction of polarization. And this light ray will be partially polarized, both component, both perpendicular and parallel, and some arbitrary component will be there. This is partially polarized. This is partially polarized. Now Brewster able to use, as the fact is known that angle between reflected ray and refracted ray is 90 degree. So Brewster used this fact to calculate this angle of incidence. So here it is the, so I forget to mention, this is the our separation plane between two medium. So plane of separation. So here you can think a medium of refractive index into, here a medium of refractive index in one. So for now you can think this is air, for now you can think this is glass, or you can think water also. So if I apply Snell's law, then N1 sin theta, so let me call this theta r, equal to N2 sin theta r. So this theta is the angle of incident and theta r is the angle of refraction. Now this side I can write 180 degree is equal to theta plus 90 plus your theta r. So theta r is basically 90 minus theta. So instead of sin theta r, I can write down 90 minus theta. So the fact Brewster discovered give us a way to replace the refracted angle with respect to the angle of incident. So it is become N2 cos theta, or tan theta become N2 by N1, or theta will be tan inverse N2 by N1. So this is your Brewster angle and the mathematical representation of the Brewster law. If N1 is air, sorry, if the medium 1 is air, then its refractive index is 1. In this case, theta going to be tan inverse N2. Now for glass, we already aware the refractive index is around 1.5. So theta is tan inverse 1.5. So it will become around 55, 56 degree. Now for water, N2 is 1.33 and theta will come, theta will be around 1.33. Now we have to calculate it using calculator. What will be the value of this particular theta? So this is the idea of Brewster law and polarization by the deflection. So with a proper angle of incidence on a particular surface, the reflected ray become polarized and we can use that. Now let me discuss one important factor. Change in intensity of light after passing through a polarizer. So that we are going to discuss in the upcoming discussion. First case, let's say we have an unpolarized light. Let's say we have an unpolarized light is passing through a polarizer. So that can be a polarization film, that can be something we call a nickel prism. Polarizer film is in actually in our good quality sunglass, it is there. in the LCD display of the desktop is there, this type of polarization film is there. Even the calculator you are using, this digital calculator, and that LCD display also have a piece of paper which is polarizer. That polarization is required there. The LCD or the liquid crystal there to visualize the image. Now, so okay, let's move on. So we are actually passing a unpolarized light of intensity I naught through a polarizer. Let's say this polarize in that direction, and light ray will come out like this. Now the intensity of the light coming out from this polarizer will be I naught by 2. I am not going to the derivation of this, but simply during explanation you can think. So this is the polarization axis, this y axis, axis of polarization. So this is your y axis of polarization. Now electric field is this is the direction of electric field. Now we can decompose this electric field into two components. So it is E cos theta. In this direction it will be E sin theta. Now this E sin theta will be vanish, E cos theta will survive. It will absorb the E sin theta anyway. I am not going to the real mechanism. Now if there are all possible electric field vector, the component along the y axis will survive, and when you take a average of it, so this is the, so we know intensity is proportional to the electric field square. So intensity will be proportional to E square cos square theta, E naught square cos square theta, where E naught is like intensity amplitude of the electric field. We are assume that all the wave has same electric field amplitude, but their angle with respect to the polarization axis is different. Now the average intensity you are going to get E naught square average of cos square theta. So you are already aware of this. Average of cos square theta and sin square theta is a half, and this is our I naught by half. So that's a crude explanation I am given. I have given that when a light ray, unpolarized light pass through a polarizer, its loss is half of the intensity, and because it's half of its kind of you can think they are part of its electric field which is perpendicular to the polarization axis is absorbed. Now move on. Second, what going to happen if a polarized light pass through a polarizer? So if a polarized light pass through a polarizer, so let's say we have a polarized light in passing in polarization plane of polarization like this. So it's basically a vertically polarized light, where plane of polarization is in the plane of the board. Now we placed a polarizer whose polarization axis is in that direction. So the light rays come out here. If this is I naught, the same intensity will come out. There will be no loss or absorption. Now again, let's say the same light is passing through a polarizer or polaroid, you can think also. So polaroid is basically a particular film. Polarizer is the film, you can think of film or nickel prism or any other means of polarization. So now this is the polarization axis. So when light ray pass through it, it will be polarized in that direction. Now initially there is no light, no electric field which is in that direction, or we can't get a component of electric field in that direction. So the output intensity becomes 0. So no light will pass come out of it. Now your question is coming in your mind that if we make the angle of polarization, sorry, yes, not angle of polarization, the angle of this polarization axis like this, we rotated the polarizer in some arbitrary angle, it is 45 degree, 30, 60. Then what going to be the relation between the light entering here I naught and light coming here I, and that's where Miller's law come into the picture. So it tell us, let's say if we have a polarized light of intensity I naught, polarized light, plain polarized light, and now we have a polarizer whose axis of polarization making an angle theta with the making polarization axis making an angle theta with this polarized light, then the intensity come out here will be I naught cos square theta. So let me again explain this. So let's say this is the some xy plane, and this is the axis of polarization, and our polarized light have a polarized direction like this. So as we drawn, it is a vertically polarized light, and angle between this uh, uh, electric field and this polarization angle is theta. So in this case, the light emitted out of the polarizer at an arbitrary angle will be I naught cos square theta. Like from here, if theta is equal to 90 degree, then you can see I becomes 0. So this is the basically this case. Sorry, not my bad. This is basically this case. And we can also check the first case when both the electric field vector and the polarization axis is parallel. That means the angle then becomes 0 degree. Then your I will be I naught only. So cos 0 will give us 1. Now if theta is 30 degree, or let me first check 60 degree. So I going to be I naught, the cos square theta, cos 60 half 1/4. So your intensity out of the polarizer will be I naught by 4. Now if it is 30 degree, so it will be 3/4 of initial intensity. And the last one, if the theta is 45 degree, so we lost half of the intensity. So this is actually Miller's law actually tell us this, how the intensity of a polarized light after passing through a rotatable polarizer changes, that is told by this law, and this is very easy, obvious. And some simple problem come from this. So basically, like they can ask, like initially we have a polarizer, and initially we have an unpolarized light of intensity I naught, which is passing through a polarizer, which can be oriented in any direction, but we know intensity coming out of it will be I naught by 2. Now after that, the light that is passing through a rotatable polarizer, which making an angle theta, the axis of that polarizer is making an angle theta with the polarization direction of the polarized ray. So what will be the intensity here? Let me call it is I final. I final will be I naught by 2 cos square theta. So this type of the thing they can give. One type of problem you can expect. Another type of question we can expect, that this is more interesting, that so we know if we have, let's say have a polarizer oriented in that direction, and if we have another polarizer which is crossed So if an unpolarized light enter here, if an unpolarized light enter here, if an unpolarized light enter here, we know here initially get 0 light. So first polarized make the light polarized in that direction, and the cross polarization will don't allow anything to pass out of it. Now let's make our life little bit hard in that case. Sorry. Um, Let me now put another polarizer in that direction, which can be rotate arbitrary angle with respect to the any of the polarizer. In we can think the angle in terms of first polarizer as well as the last one. Now what will be the output intensity and how it is depend on this theta. So before going there, so let me check this. If so, let me check the angle with respect to the last axis. If the theta is 0, that means both the polarizer are like this and initial one as it is. It is obvious the intensity will be 0. Again, if this theta is 90 degree, that means it is the middle one is like this, and the last one is obviously it is we can the last and first one we cannot move. The middle one or third one we can't move. So obviously it is like identical to the first case. So light ray which is polarized in that direction go out, I enter into it. It will be here after passing through this polarized 3. It will be again vertically polarized and it will be cross blocked again here. But in the first case, the middle polarizer already blocking the light here. It is not allowing any light, and obviously we are expecting nothing in the after the second polarizer. But here also, in this part we already discussed that intensity will be again 0. So the magic will happen in between. So here we can see two minima at 0 angle it is also minima and 90 degree it is also minima. In middle something will happen. So let me discuss. Let me now make a relation between this I naught and I output here. I output as a function of theta. So I have to call it I prime basically, or I final will work also. Okay, it's not that hard anyway. So let's say angle is given with respect to the last polarizer. So that we know this angle is theta. Let us consider like this. Now we can apply a set of Miller's law here. So if intensity entering into it is I prime, then so you can think like that. You can think this one as a this one as a first polarizer which is polarizing the light, and this one you can think this is the analyzer which we using which we are analyzing the light. So here when intensity come out of it, I final which is going to be I prime cos square theta. So if the I prime is entering here, here using Miller's law, I prime cos square theta will come out. But what is this I prime? So this is the important fact. What is this I prime? Now if I naught is going here, we know I naught by 2 come out here. So I am making some mistake anyway. So let me correct my mistake. So light intensity after passing through this polarizer 3, here is I prime, and light intensity after passing the first polarizer is I naught by 2. You can think, you can give some notation here, but let me consider is I naught by 2. Now again with here we can, in between 1 and 3, I can again apply a Melas's law. So I naught by 2 entering, I naught by 2 going and falling here. I naught by 2, you can think something like I initial or something like that, and or I1 which is falling on I Polaroid 3, and what will be the intensity there. So the angle between this and this, so I have to first calculate. So we know angle between last polarizer and the middle polarizer is theta. Again, the last polarizer and first polarizer is 90 degree apart. Then angle between the middle polarizer and the first polarizer is this phi, which is this phi is nothing but, then from the geometry it is 90 minus theta. So this angle is important. This is 90 minus theta. So now I know the angle, I can apply the Melas's law between first and the middle polarizer, or first polarizer, and I am marking it as 3, polarizer 3. So again I prime actually, which is coming out from the polarizer 3, is I naught by 2 into cos 90 minus theta plus square. So it will be I naught by 2 sine square theta. Now we already show that in the last pair, again we have to apply a Melas's law, where the angle between the polarizer and analyzer, or between the two polarizer is theta. So that is given in the question like that. So there we see the I final is I prime cos square theta. So finally we can write I naught by 2 sine square theta cos square theta. Now for you, I have a question, like you can find what will be the angle, what will be the theta, such that we can get IF maximum one. So answer is that theta will be 45 degree. The middle polarizer have to be 45 degree with respect to actually any of the polarizer. Then we can get maximum intensity out there, but that you have to find. So it is very easy to find anyway. So just take a derivative and find out, solve for the theta, set it 0, solve for the theta, you will get this value. Now let me leave it. Now let me check some problem, basically what we are getting. So let me go to the board and let me first check the problem. So this problem is telling when an unpolarized light is incident at an angle 60 degree on a transparent medium of air, or on a transparent medium from air, the reflected ray is completely polarized. The angle of refraction in the medium is. So there is some kind of a medium. So let me back to the board. So angle of incident they given is 60 degree. And light is coming from air and reflected completely polarized. So let me back to the board again. So this is air, light rays coming from air, falling on the interface of the medium and reflected. The reflected ray is 100% polarized. So this is a case of polarization by reflection. So that means we are studying basically Booster law. So we have to take help from Booster law. So they want to know the refractive index of this medium, and here they given refractive index is this is air medium, therefore refractive index will be 1. So we know theta is basically tan inverse n2 by n1, or here n1 is 1, so tan inverse n, or n is tan theta. So it is tan 60 degree. So then I have to check what is value of this refractive index. So then it's easy. We are getting in as root 3. So let me check the answer there. Okay. Oh, so they want to know the angle of refraction in the medium. Okay, okay, not the refractive index of the medium. Anyway, my bad. So we got our refractive index anyway. So we can apply Snell's law again. So first we apply Brewster's law. Now Snell's law give me n1 sin theta 1 is equal to n2 sin theta 2, or which is the angle of refraction basically. Or sin r is half, that means it is 30 degree. So the angle of refraction I am getting as 30 degree. So this is one type of question we see related to Brewster. So that was correct. Now let's check another problem. It is telling an unpolarized light of certain intensity passes through a combination of two polarizers whose transmission axes are 30 degree and 90 degree respectively with respect to some horizontal axis. A third polarizer, which is transmission axis 60 degree to the horizontal axis, is placed between the two existing polarizers. The ratio of output intensities with and without the third polarizer is. So that's a very good question. So here initially we have a polarizer whose, so let me check, this is some horizontal axis. There is one polarizer which is making 30 degree angle 30 degree with respect to, let me call it polarizer 1, with respect to that horizontal axis, and another polarizer which is making angle 90 degree with the horizontal axis. Now angle between both the polarizer is 60 degree. Now then we have polarizer P1, another polarizer P2. Now we know angle between them theta is 60 degree. So if unpolarized light is passing through this I naught, we know after passing through P1 it is obviously I naught by 2, and after passing through this P2 it will be I naught by 2 cos square theta. So I naught by 2 cos 60, cos square 60, that means 1 by 4. So I naught by 8 is our final intensity when two polarizer is there. Now we are going to insert another one in the middle. So that make our life little bit hard. So we are considering, let me consider that this is my P1. So P1 is making an angle 30 degree with the horizontal plane, and the third polarizer has a transmission axis which is 60 degree with respect to the horizontal axis. Now obviously the angle between both the polarizer will be 30 degree. So let me do it step by step. Initially unpolarized light of intensity I naught entering the polarizer P1, it is coming P naught by 2, sorry my bad, I naught by 2. Now there are another polarizer in the middle. The axis between the angle between both the axes of both polarizer P1 and P3 is 30 degree. Then the light ray coming out here will be I naught by 2 cos square 30 degree. So it will be root 3 by 4. So 3 I naught by 8. Now again light ray have to be passed through another polarizer. So with respect to the horizontal axis, the P2 is making an angle 90 degree. So that means the angle between P3 and P2 is this. Which is again 30 degree. Which is again 30 degree. So cos square 30 again give me 3 by 4. So it is 9 I naught by 32. So this is basically intensity in second case, and intensity is first case was I naught by 8. Now they want to know the uh, they want to know the ratio of the ratio of I2 versus I1 or I1 versus, let me check, ratio output intensity with or without third polarizer. So with third polarizer is I 9 by 32 I naught, without is I naught by 8, I2 by I1. Is 9 by 4. Okay, so let me check the answer. So 9 by 4 is there. Okay, it's worked. Now the last one. When a Polaroid sheet is rotated between two cos Polaroid, then the transmitter intensity will be maximum for rotation of which angle? So we already discussed the answer. It is 45 degree. So if you want, I can let's prove it there anyway. So I am avoiding the proof for this. So let me prove it. Okay, let me back to the board. So we already discussed that final intensity will look like this: I naught by 2 sine square theta cos square theta. I final going to be I naught by 2 cos square theta sine square theta. So we have to take a messy derivative here with respect to, we can, this I naught by 2 is a constant. You can think this as I prime and then cos square theta sine square. So no problem. So dIf d theta we need to do. So okay, I can apply some trick also here before doing the derivative. Okay, better to bring first 4 here. So let me do something. So let me apply a trick. So I naught by 4, then it will be 2 sine theta cos theta, that kind of a square kind of a thing. So it will be I prime by 4. It really doesn't matter what is the font part. Sine 2 theta. Sorry, my bad. Yes, it's sine 2 theta. Now if I take the derivative df d theta, so let remove don't consider the constant part. It will be cos 2 theta into basically 2, and everything will be 0. So cos 2 theta equal to 0, which is equal to cos 90 degree at least, and 2 theta is 90 degree and theta is 45 degree. So far so good. So at theta become maximum at 45 degree. So these are the type of question you going to face when you look into the competitive different type of competitive exam. So I hope I completed the major type of question. So thank you. Let me check the answer and thank you.